All right, in this chapter, we're going to talk more about acids and bases. So first, we'll talk about some properties of acids and bases and some of the definitions of acids and bases. Up until now, we've just been talking about one form of acids and bases. We're going to talk about a different way of how to explain acids and bases. Then we'll talk about how water really is the reason why we have an acid and a base. And water is actually both an acid and a base. It's what's called amphoteric, has both properties. Then we'll talk about what strong and weak acids and bases are, how to do some pH calculations, weak acids and bases, some of the titration calculations, which we've kind of already discussed in the stoichiometry chapter. And then we'll talk about a buffer and what buffers are. All right, so the first definition of acids and bases that we've been using up until now is the Arrhenius acids and bases. And Arrhenius is basically an acid is anything that when it ionizes, it forms an H plus ion. All right, that's pretty straightforward. So pretty much any of these are considered an Arrhenius acid because when they dissolve in water, they split apart, all right, into an H plus ion and whatever anion you have. Here we have 2 H plus ions for every mole of sulfuric acid, and here there's 3. So if you take HCl and put it in water, it ionizes into H plus and Cl minus ions. And that's what we were calling an Arrhenius acid. Arrhenius base is just the opposite, and it's just as simple. Anything that ionizes into hydroxide ions is what we call an Arrhenius acid. So you take sodium hydroxide, throw it into water, you get hydroxide ions. So also like potassium hydroxide or lithium hydroxide. All right, so Arrhenius acid bases, way you describe it, is pretty much for most acids and bases, but it doesn't explain everything. Perfect example is ammonia. All right, well, by looking at this, you would think it would be an acid because like we said, anything that has H's really is an acid. However, this does not ionize. Remember, an Arrhenius acid is something that ionizes into H plus ions. This does not form H plus ions. Okay, so this is not an acid. In fact, if you take ammonia and you put it into water, you have a pH greater than 7. So that would imply that ammonia is a base. So why is it a base? Notice there's no hydroxide here. So Arrhenius method of defining acids and bases don't always work. So they had to come up with another way of explaining acids and bases. And that was Bronsted-Lowry. Okay, it's actually called the Bronsted-Lowry acid base. I don't know why your book just calls it Bronsted, but it's technically a Bronsted-Lowry acid and base. Okay, their way of talking about it is more of a chemical reaction way. It's based off of a chemical reaction. And in every reaction, you have both an acid and a base, an acid plus a base. Okay, and it's all based on the point of view of the proton. You have a proton acceptor and a proton donor. So anything that donates a proton, we call an acid. Anything that accepts a proton, we call a base. Okay, so if you were to look at this equation down here, we have ammonia and we have hydrochloric acid. Okay, when you do the reaction, what happens is ammonia accepts the proton. So this is the proton acceptor, we'll call it PA, and this is the proton donor. It donates the proton. So if this donates the proton, this is acting as the acid. If this accepts the proton, this is acting as the base. Okay, and the way we know that is by looking at the products. Look what happened. The NH3 accepted a proton and went from 3 protons to 4 protons. And look, it also gained a plus charge. Why did it gain a plus charge? Well, it gained an H plus ion. So this H plus comes over here and it brings everything over to it. It brings an extra hydrogen and it brings that charge to it. All right. The Cl loses a proton, and since it's losing a plus charge, it becomes a negative charge. Okay, so these charges are going to become important. Make sure you follow these charges. Whatever loses the H becomes more negative. Whichever gains the H becomes more positive. Okay, and on this side of the equation, this is actually called a conjugate acid, which I believe we'll look at in the next few slides. And the Cl minus is what's called a conjugate base. So we have different names for everything on each side of the equation. All right, conjugate acid, conjugate base. Basically, how you know this is whatever if the hydrogen left the ammonia here, the ammonia is the base, it's the exact opposite on the other side. The ammonia is part of the acid. The Cl is part of the acid on this side, so it's part of the base on that side. Okay, so here they kind of talk more about it, but when a Bronsted array donates a proton to another substance, the remaining substance is called a Bronsted base. So here's the acid, it donates the hydrogen. So what happens? It goes to an H3, you gain a hydrogen, and you also gain a plus. So that's why we have H3O plus. Okay, and the Cl loses the H and the plus, so it loses the H and the plus, so it becomes a Cl minus. HCl here is the acid on this side, therefore it's the conjugate base on this side. The water is accepting the proton, therefore it's the base on this side, so therefore it's the conjugate acid on that side. Okay, now here's the ammonia case. This is why Bronsted-Lowry even did this to begin with. All right, ammonia acts as a base. How do we know? Because it has a pH greater than 7. It's kind of like they kind of figured this out after they did the experiment. So they took ammonia, they put it in water and saw that it was basic. Well, they had to somehow explain this. So how they explain it? Well, they explained it by the base was accepting a proton from the water. So water donates a proton to ammonia. So ammonia becomes NH4 and it gets a plus charge. Water loses the hydrogen and the plus charge become OH minus. So notice you are forming hydroxide ions. And what did we say is a base? Based off of the Arrhenius analysis is that anytime you start forming hydroxide ions, you are basic. So that's basically what's happening. All right, so that explains ammonia. Okay, so here are some really quick, easy problems. All right, understanding acid-base conjugates, especially the conjugates. Okay, so if you have HNO3, what's the conjugate base of this? Well, this is acting as an acid. It's going to donate its hydrogen to whatever. Let's just say water. So if it's acting as an acid, on the other side, it's the conjugate base. So what's the conjugate base? It should be NO3 minus because it lost one of the protons. Okay? So a conjugate base is always losing a proton. Here I have O minus 2 and I want the conjugate acid. So if I want the conjugate acid on this side of the equation, it's acting as a base. So it's going to accept the proton. So it's going to become OH minus. Okay, we'll do one more and then you can do the last one on your own. HSO4 minus, we'll do both of them. The conjugate base, so it's acting as an acid on this side, so it's going to donate a proton. It gets rid of the proton, so this gets one less proton, and it gets one less positive charge, so that means it gets another negative charge, so it goes to a 2 minus. And then finally the HCl3 minus, it's acting, I want the conjugate acid, that means it's acting as a base, so it's going to accept the proton. So we're going to add an H plus to this, so it becomes H2CO3. And the minus charge balances out with a plus charge. Okay. Now this takes a little bit of practice because you're kind of thinking backwards and forwards. It's an acid on one side, it's a conjugate base on the other. I'm just kind of explaining it straightforward, but you need to spend some time on these problems. Okay. So there are the answers. So here's another problem you can kind of do on your own. Label the acid, label the base, label the conjugate acid, label the conjugate base. All right, just like how we did. Like here, I'll do the first one. All right, here's HF and here's NH3. Well, based on the equation, the F minus is losing the proton, so this is acting as a donor. So this is the acid. The ammonia is accepting it, so this is the base. The F minus now on this side is the conjugate base, and the ammonia right here, the fluoride is the conjugate base, the ammonia is the conjugate acid. All right, see if you can do B on your own. All right. Okay. 12.3 now talks about water. Water is what's called amphoteric, meaning it has both acid and base properties. Like the word amphibian. Amphibian means it could, it's an animal that can live in both water and in the air. So ampho is a, I think it's either Greek or Latin, meaning both. Okay, so most acid-base chemistry that we encounter always takes place in water, meaning aqueous solution. All right, and water can act as both an acid and a base. All right, And what happens is you have what's called this auto ionization. Let me just see what this book, what this page says. Even pure water has a small amount of acid and base. So water itself even kind of acts like an acid and base. So that means one hydrogen from one water molecule is donated to another water molecule. And you kind of get these two ions in your solution, but it's a very, very, very small amount of it. Okay, very small amount of what's called hydronium ion. H3O plus is what's the hydronium ion, and the hydroxide ion. And they have actually figured out what the concentration of this is. This is the concentration of H3O plus OH minus. It's what's called auto ionization. That means water itself is ionizing itself. Okay, and the concentration could increase if you start adding more hydronium ions. All right, so this equation is going to become important, and I believe they do some calculations. So these brackets mean concentration. So this is the H3O plus is acid concentration, and this one is your hydroxide concentration. Hydroxide concentration. Okay, so here's a problem. If the problem says you have a concentration of hydronium ions equal to 0.10 molar, what is the hydroxide calculation? I'm sorry, the hydroxide concentration. Well, we know that the hydronium times the hydroxide is equal to 1.00 times 10 to the minus 14th. So if this is equal to 0.10, I'm solving for the hydroxide. 1.00 times 10 to the minus 14th. So my hydroxide concentration equals 1.00 times to the minus 14th divided by 0.10. All right, so if I were to do this on the calculator, I'm going to put on pause and come back in a second. All right, the answer equals 1.00 times 10 to the negative 13th. Okay, and you can basically see that's what we do, and there's the answer. Okay, so this is one of the calculations that you're going to have to kind of know. I'll go back to it. On the final exam, you will be given this calculation or this equation, plus there are two other equations that we'll talk about throughout this chapter. All right, so when we get back, we will start talking about strong acids and strong bases. We will come back to those types of calculations as well.